Okay, so back to our application stuff, right? So there's a lot of things we do in physics. Go ahead and click close, phone should be away, all that stuff, please. There's a lot of stuff we do in physics that's modeled by quadratics. For example, when we talk about projectile motion, right? So there's a reason for this, because if you drop an object and it's subject to gravity and it falls, it's accelerating at a rate, well, it's accelerating, the equation for calculating acceleration is such that the rate of acceleration is always going to be proportional to the square of time, the amount of time it's been falling, okay? And so what that means then is you're always, whenever you're doing any kind of a free fall, projectile motion and free fall are the same thing. When you shoot it, if we ignore air resistance, which we're going to do, air resistance makes it pretty complicated. But if you ignore air resistance, so say we do these experiments on the moon, for example. If you were to shoot the projectile out of a cannon or something, and the ball were to fly through the air and land somewhere, it's true that the arc that the projectile would make, hold it away please, hold it away. The arc it would make would be parabolic. And so if you wanted to describe the path, yeah, it's a parabola, so it would be a quadratic function. But more importantly, probably, when you look at the motion of an object that's in free fall, when you look at the height of the object as a function of time, that's a quadratic function. Okay, and so I'll have you guys at some point, either I will or Mr. Cooper will have you in physics, and we'll talk about this stuff in more detail. But when you calculate the components of an object in free fall or in projectile motion, what you're always going to find is that the horizontal component of the velocity stays constant. So if you were to look, and you might even notice this, like if you're watching a football game from the blimp cam or something, right? They focus down on the field and someone throws a pass. What you'll always see is that when the ball goes through the air, constant speed, it doesn't change. Seen from above, if you're looking at just the horizontal motion, any projectile has constant velocity. But vertically it doesn't, right? If you were to look at an object, let's say I'm looking straight at a ball that's being thrown at me, what I'm going to notice is I don't see the horizontal component, but I see the vertical component. It starts off fast and then slows down and hits the apex and then speeds up on its way down. Exactly the same as if I threw a ball from the air and caught it, right? When you combine those two things, that's what gives you that parabolic trajectory, okay? But no matter how you slice this, I guess the point I'm trying to make is if you want to look at the height as a function of time, or you even want to look at the path that it describes, they're both quadratic functions, right? So they're applications of the stuff that we're talking about right now. So let's look at this example here. If you drop a penny off the Empire State Building, here's the model for that. This model's height as a function of time. So H stands for the height above the pavement at the base of the building, right? The sidewalk, let's say. And T is the amount of time that the penny's been in the air, measured in seconds. Okay, so we were started to look at just quickly analyze or evaluating this function to get a feel for what the function is doing. If I plug in 0, time equals 0, the height is 1250, which makes sense because we're starting the clock, or starting the stopwatch in the instant that we drop the thing. So time 0 is when we hit start, right? And it's starting at 1250 and it's gradually going to lose elevation. The height is going to decrease with time then. If we plug in a value like 2, we got an answer of 1186 feet. Still pretty high, but it's getting less and less, right? So our question here is, how long would it take to strike a 6-foot tall person? Okay? So we're trying to solve for, what's the variable we're trying to find in? If the question is, it's asking how long?
T.
T, right? How long means T equals what? Okay? So we've got this model. Here's our function, height as a function of time. How are we going to use this model to solve for T? What does this part mean right here? Let's interpret this. How long does it take the penny to strike a 6-foot tall person? What's that telling us? The height. Okay, what's the height equal to? 6, right? That's what that's telling us, isn't it? That's telling us that h equals 6. So what am I going to do then to my model up here? set h, and h of t, all this means, how come I have the of t there? Well, because it's a function. It's just reminding us that we're inputting time to calculate h, right? But this is the same thing as just writing an h down. It's just function notation, right? So we're setting the value of the function h equal to 6, and that's giving us an equation, right? Okay, so let's write that then. So we're going to get our function negative 16 t squared plus 1250 equals 6, right? There's our equation that we're going to solve. That looks an awful lot like a regular old quadratic equation that you're used to, right? So what do we do if I want to solve for t? Let's give it a show of hands here. Somebody got an idea? Okay. How come? You're right. How come? I'm trying to isolate t, aren't I? And we see that because I'm solving for t, and there's a single t that I can point to, so I can use inverse operations and solve for it, right? Okay, isolate it. So we're going to subtract 1250, and that's going to give us negative 16 t squared equals negative 1496.
What?
1290 or 1196.
Huh?
Oh no, 1244. What am I doing? Oh, I don't know.
Thinking about the scores and
I was thinking that. I don't know what I was thinking. 1244. Okay. Divide by negative 16. Very good.
Oh, you're so smart.
So those cancel, and I'm going to get t squared equals negative over negative is positive, and I can probably reduce that. Let's see, 4 goes into both of those. The 16 is a question. 1696, 108.
Calculators out.
It doesn't. You're right. But we could reduce it to, we could divide both by 4, right? And we're going to get, if I divide those both by 4, I'm going to get 311 over 4. I'm kind of stuck there, aren't I? Say it again. Negative over negative is positive, right?
Yeah.
Those were both negative, so now they're positive.
Just
Right. And then I'm just going to square root, aren't I? Right? If I square root both sides, it cancels the squared, so what do I get? T equals, okay, but mathematically, plus or minus, okay? Plus or minus the square root of 311 over 2, right? And so that's going to give us something like 16, what about like 17.6, something like that. What is that real quick? So divide by 2, so we get about like 8.8-ish, something like that. What do you get?
8.817, blah, blah, blah.
What is it again?
8.817.
Okay, so about, I get 2 answers. I'm either going to get, if I take the plus, I'm going to get about 0.81, you said?
Yeah.
0.81, blah, blah, blah. Okay, so 0.81 roughly, or what if I take the minus? We get negative. Hang on a second here. Something. Okay.
What would be negative?
Yeah. Okay. So it's going to be negative that. Right?
Because we're not doing eyes anymore.
Okay. Yeah.
It's
8.81. Yeah. Right. Right.
Did he not write that? Oh.
No, I wrote 8. I
Right.
I'll just make it 8.8. That's close enough. Well, which answer are we probably looking for? The positive one, right? Okay. So there's our answer. But just really quick, is the negative one ridiculous? What's the negative one really mean?
It's good. I don't know.
Okay, yeah. It's now think about this. It's the
It's following.
I guess these are kind of the physics gods because we're doing some physics here. But physics gods and the math gods, both they don't have much of a sense of humor, but they're very smart, right? They're going to give you what you ask for. You be careful what you ask for, though. Did we really ask for, now, we're trying to fit this physical situation up here, right? That's to the mathematics, right? To a mathematical model. And by setting the height function equal to 6, did we specify that that's how long it's going to take for the penny to hit this guy on the head after he drops it? I mean, not really. All we said was, to the math gods or the physics gods, was, what's the time when that penny is going to be at a height of 6 feet? The math gods and the physics gods know nothing about pennies or buildings. All they know about is physics and math. So if we give them this function and we ask, when does h equals 6, here's how they're going to think about this. They're going to think about this in terms of maybe a function, right? So they're thinking about it like this. They're thinking about, if I were to graph height as a function of time, the part that we're interested in is going to look like this, right? If I graph this function, negative 16t squared plus 1250 equals 6. If I were to graph that, what I'm going to find is it's going to look like this. Right. We're interested in the part where, now this is not drawn to scale, we're interested in the part where if that's 6, we're interested in the part where the height is 6, and the coordinates are going to be in the form th here instead of xy, right? Everybody agree? Okay. So the x coordinate at that point is 0.88, and the y coordinate is 6. Okay? But does a parabola look like that? That's only half a parabola, right? This parabola, this particular parabola, is going to have its vertex right there, and it's going to also exist over on this side. So there's going to be another place, if I look at this function, there's another place right there where the height is equal to 6, and the value of t is negative 0.88 at that place on the function. Okay, so that seems kind of weird. It's in a negative time. Negative time's ridiculous, right? You want me to show you negative time?
Yeah.
I'll show it to you right now. Okay, I'm going to snap my fingers twice. We're all time travelers. You're traveling through time right now.
That's not what I mean.
Well, that's what a time traveler is, though. To travel through time means you're going to move through time. Okay, so I'm going to snap my fingers twice. Okay, so here's the first one. Ready? Okay, relative to the second snap, when was the first snap?
Wait.
Yeah, just tell it's relative. So I can arbitrarily set time to equal 0 at any time I want to. We usually do that at the present. That's like we're dragging along a moment in our lives where we're going to say, right now it's time 0. But we don't have to. There's no reason we have to do that. It's just convenient for us because we call that the moment, right? The present. Future is when time is going to be positive. What's the past? Time's negative. That's all it is. Negative time just means in the past. So if I snap my fingers 3 seconds apart, relative to the second snap, the first snap happened at a time of minus 3 seconds. So negative time is no mystery. It just means, so negative 0.88 seconds means 0.88 seconds before I dropped the penny, right? Okay, but as far as the math and physics gods are concerned, that penny didn't start its motion when I dropped it. Maybe this happened instead. Maybe somebody shot it up from the ground, and it rose up in the air, and right when it got to the level of the person's fingers, he snapped his fingers as it started to fall, and that's when we started the clock. Is there any difference between that or me dropping the penny? No difference at all, right? Either way, the penny's at rest when we start the stopwatch. Agreed? So if that were the case, if we had launched this penny up from street level, when would it have passed? When would it have been at a height of 6 feet? It would have been there twice. It would have been there once on the way up and once on the way down. So the math and physics gods, they're giving us some interesting information. It's just not what we were looking for, right? The context of our problem, we were asking for on the way down, when is it going to be at 6 feet, right? But that might be interesting too. It's just not what we're looking for, right? Make sense? Okay. All right, what about this one? A toy rocket is launched vertically upward from a 12-foot platform with an initial velocity of 128 feet per second. Once again, they're giving us a model. Height h as a function of time. So h is the output, time is the input, right? Height is output, time is input. Here's our model for that. Okay, notice it's quadratic again. Okay, so let's write that down. Okay? Now, if those were x's, you could tell me some things about this function already, couldn't you? It's quadratic, so it's a parabola. What are the values of a, b, and c? Because it's in standard form. -16, 128, and 12, right? Okay? So does this parabola open up or down? Down. How come? A is negative. Okay. So there we know something already. So if we're trying to figure out how long it's going to take to reach the ground, what are we going to do? Where's the ground? It's being launched from a platform that's 12 feet high, but it's going to hit the ground. Okay, is it 12 though? Because what is h measuring? H is measured from the ground, right? The platform is already at 12, and that's why that 12 shows up in the model, because that's the initial position, right? We'll talk about that in physics in a couple of years. So, what's the height of the ground again? So what am I setting h equal to? 0, yeah. Okay, reach the ground, in other words. Reach the ground corresponds to h equals 0. So we're just going to set this function equal to 0 and solve. That's right. Okay? So now we can flip into math mode. We use the physics to set up this equation with our model, but now we're just cranking out a quadratic equation like you've been doing. So what can we do with this? If I'm just trying to solve this equation right here, what are some things I should probably do? Take something out maybe, right? I could take out a 4. In fact, I could take out maybe a -4, how about? Right? So if I factor out a -4, what am I going to be left with?
4t.
4t squared minus 32t minus 3. Okay. Equals 0. And I could divide by -4 and just get rid of that, because I'm just trying to solve the equation, right? Now what? Okay, I mean, I could just jump right to the quadratic formula, right? Because it looks like, I mean, I'm not going to want to, if we went down the list, I can't isolate x. It's really not a convenient one for me to complete the square on, because I'm stuck with a 4 there, right? And factoring it, is factoring going to work? Well, what we maybe could do, you could maybe salvage it by factoring. It's not going to work. But you could convince yourself of that pretty easily if you just calculated the discriminant, because we got to calculate it anyway to do the quadratic formula, right? So what is b squared minus 4ac? I'm going to get 32 squared. Well, so what's that going to be? 980. I hope, is that right? What's that going to be?
1024.
1024. There we go. Okay. Minus 4 times -3. Well, I'm multiplying a negative times a negative there, right? So look what that's going to do. That's going to make that a positive, right? And so I'm going to end up getting 1024 plus 48 is 1072.
Yep.
So the discriminant is positive. Is it a perfect square? Not a perfect square, right? 1072 is not a perfect square. So we know it's not going to be able to factor it in, right? Because we're going to get irrational zeros. So we'll just push on and do the quadratic formula. So we're going to get t equals -b, so 32, plus or minus the square root of 1072 all divided by 2a, so divided by 8. So if I split that up, 32 over 8 is 4 plus or minus, let's see, if we wanted to do, we could probably break this down a little bit. 1072 is going to be 2 and 536, 2 and, what's that going to be? 268, all right? 2 and 134, 2 and 67, you're right. And then 67, I bet, we're stuck there, I bet, huh? I'm guessing. 67's gotta be prime, huh?
Yeah.
Okay. So then look, we get couple of twos, single 67, so that's gonna give me plus or minus, there we go, good, we're gonna get 4 outside times the square root of 67 inside over 8, 4 over 8 reduces to 1 over 2. So I'm getting two values here. I'm getting t equals 4 plus or minus square root of 67 over 2. So if I take the plus, give me 1 second to give me, you guys can do the calculator real quick. Something
Wait,
like,
what was it for? Other four.
say it again?
Oh, 4 over 8. Yep.
Yeah, so like 8.1 kind of a thing, between 8.0 and 8, close to 8.1 for one of them.
What? Oh.
About negative 0.1 for one. A little bit less probably. 8.0 something.
8.0 max.
Yeah, about 8.1, and then it's going to be, for the minus, I should do that. For the minus, we're going to get negative about 0.09, so it's going to be about 0.1.
Yeah.
So those are the two values. Okay, so interpret those. Which one do we want? Want the positive one, right? Okay. So how long will it take to reach the ground if we launch this thing up? It's going to take a while. It's going to take 8.1 seconds. What's the negative 0.1 doing? What's that telling us?
When you throw it up.
Okay, if we launched it up from the ground so that it passed by the platform with a speed of 128 feet per second, then how long would it have taken to get from the ground up to the platform? Because this would be the same thing as saying, like, instead of shooting this out of a gun or something, what if I had an empty pipe and we shot the projectile up from the ground and it went through the pipe on the way up, right? Same deal, right? As far as we're concerned, the outcome's going to be the same. How long would it have taken to get from the ground to the empty pipe? About a tenth of a second. Okay? Right. How could we find out? Questions so far? Okay. I want to see if we get one. Okay, yeah, here's a good one. Okay. So what's the maximum height reached by this ride? So here we've got this, some kind of a roller coaster, and the height of the roller coaster is modeled by this function. Okay, so it's just kind of gliding up, it gets going real fast, and then it coasts up the hill and down the hill. What's going on, okay? We want to find the maximum height. How am I going to do that? Okay, what if I graph this thing? You tell me now, I want you to just kind of think outside the box here for a second. Think about this strategically. If I were going to graph this function, and this is one of the things, so everybody I know, okay, you'll wake up, you guys see this? So this is something we're talking about a lot in physics, or in calculus, maybe physics too. I mean, it depends. I know I'll teach you calculus, but I don't know about physics, but we'll talk about this stuff in both of those classes. When you're looking at functions like this, one of the things you want to do as a mathematician or a physicist is you want to train yourself to think about what the graph would look like if I were to graph the dependent variable on the vertical axis and the independent variable on the horizontal axis. That tells us a huge story when we can make that graph. So if I'm graphing this, and we've got, this is h, and that's t, we'll just substitute y and x, right? I mean, we're used to seeing y and x. What if we had y equals negative 16x squared plus 101x plus 10? A is negative, right? So the thing is opening down, isn't it? Okay? So then this is going to look like something like that. Agree? I'm gonna get enough, and even if I don't worry about where it is on the HT plane, we know it's a downward opening parabola. If we're measuring height on the vertical axis and time on the horizontal axis, the coordinates of the vertex up here are gonna be a time and a height, right? Okay, isn't that the place where the height is a maximum? Okay, that's a pretty unique place on that parabola. What do we call that place? The maximum, right? It's the vertex, and it's a maximum because it's opening down. So by finding the vertex, we'd be answering this question, wouldn't we? Isn't the maximum height, like the maximum y value in this case, if it's opening down, that's got to be at the vertex, right? So we can do this. We have the mathematical tools to do a question like this. All we need to do is find h and k, because that's really all those are, isn't it? H and k. Don't confuse h here with h there, though. That's kind of a bad choice, right? They're just the coordinates of the vertex. So what are the values? This is in standard form. So what are the values of A, B, and C? Negative 16, 101. We don't even really care about C, do we? Because we just want to find H and K. So how do we find the x coordinate of the vertex? So I'm just going to call it B sub x. That H is going to mess you up. I'm just going to do it this way. You're going to look at these notes, or you're going to be confused by that. So we're going to call this V sub x and V sub y, x and y coordinates of the vertex. So V sub x would be negative B over 2a, right? So that's going to give us negative 101 over 2 times negative 16 is negative 32. Well, that's going to be just a little over 3, right? What is that as a decimal, somebody? 0.15. Okay. Roughly 3.15. Okay, so that's going to be a time, isn't it? Right, so that's the time coordinate of the vertex. How do I find, plug it back in to my function right here, don't I? Right, if I want to find V sub y, right, I mean, you know, the y, it's really just a height, isn't it? That's going to be h of 3.15. So I'll plug it into my function. I'm going to get negative 16 times 3.15 squared plus 101 times 3.15 plus 10 if I plug it back in up there. What do I get if I do that? I'll do it this way, 3.15 squared times negative 16 plus 101 times 3.15 plus 10. 400 and, okay, so roughly 487.
Oh, wait, no, I did it wrong. I forgot to put negatives.
Okay, I'll go back.
Yeah,
Okay, so say it again. Okay, so I'll just do 169. That's close enough. So that tells us everything we need to know. What are they asking? What's the maximum height? 169, right? When does it reach the maximum height? When t equals 3.15. So 3.15 seconds after launch, it reaches maximum height. Okay, make sense? That's pretty cool that you can do that, right? That's pretty amazing. And there is a lot of stuff you can do with quadratics. Just knowing your way around a quadratic function and be able to model quadratics and solve quadratic equations gets you a lot of mileage
Is that a
in
9 or
physics.
7?
Say it again.
Is that a 9 or 7?
That's a 9. Okay, we're out here in 3 minutes, right?
Yeah.
Okay, so let's just look at this one. So how could we do that? Now, we won't do the problem, but you tell me, how could we do this? Eve is jumping on a trampoline, her height h at time t is modeled by that function, right? So the question is, would she reach a height of 14 feet? What could you do? Find the vertex, right? All I'm trying to find is the output of the vertex, right? The y coordinate, in this case, the h coordinate of the vertex, right? So I could just do, we could probably do this really fast. So if I wanna find, what normally we'd call h, so it's gonna be the t coordinate of the vertex, not the x coordinate. It's gonna be negative b, so negative 20 over 2 times a, over negative 32 is, what is that, negative 5 ace? A positive 5 ace. So that's gonna be 0.6125. Okay. Seconds. Okay, and if we plug that back into the function, h of 0.6125 is gonna give us back some value if I plug that in.
It's just 625.
So 625, yeah, you're right. 625. Okay, if I plug that back into the function, that's gonna give me the height. And so let's say that height is bigger than 14, is she gonna get that high then?
No.
So if the y coordinate of the vertex, the h coordinate of the vertex is like 14.5, is she gonna reach a height of 14?
Yeah.
Yeah, on the way up and the way down, right? What if the vertex has an h coordinate, so the second coordinate is like 13.5? No, then she peaks out at 13.5 and she wouldn't get there.
She would reach 12.25.
12.25, okay, so we know so we know the vertex has coordinates 0.625, 12.25, so the answer is no, right? That's the highest she gets. That's gonna be her max height, okay?